Brilliant.
So
Okay.
I see no need to promote them separately. Okay, so I'm starting, okay?
Yes,
Okay, welcome to the session of functional encryption of Encrypt 2020. So the next talk will be on gadget-based IN-true lattice trapdoors. It's a joint work by Nicholas Jennings and Bayu Lee, and Nick will give the presentation. So Nick, over to you. Can you share your screen? Yeah.
All right.
You need to maximize.
There we go. The Zoom bar is fighting me. Okay.
Yeah, looks perfect. Yeah, please. Sure.
Thank you for coming. This is joint work with Bayu Lee. Okay, so it's a compressed version of the talk, so it's going to be a little fast and furious, but let's get to it. So in the title, it's gadget-based trapdoors for iron-true lattices. To have a trapdoor, you have to have a one function. And in this case, it's going to be the ring SIS problem. So this problem, it's going to be defined by some random vector of polynomials with coefficients modulo q. We always call this A. The modulus here is pretty small, so some small polynomial in n, where n is roughly our security parameter, and it's also the degree of the polynomial ring. So we're going to mod out by some monic irreducible polynomial f of x, and we're going to take these coefficients modulo q. And also the length of the vectors in C. It's like log base 2 of the modulus. Okay, so this problem, it's an average case problem. It says for some uniformly random A and some target T. This T can be worst case. It can be 0. That's how most of us were first introduced to the problem. But you can pick your favorite T. It still has to be hard. And to solve the problem, you have to find a vector of polynomials x, and each of the polynomials in this vector, they have to have small entries. Entries much smaller than the modulus q. Okay, and the same thing in words. Okay, so an SIS trapdoor is really anything we generate this matrix A, or this vector, in this case A, together with it, such that it's easy to invert this function. In the literature, we usually write this as A inverse, where the two inputs are the target and the trapdoor information tau. And really, I say it can be randomized in the slide, but it's always randomized. We're going to be doing some like discrete Gaussian sampling over the pre-images for each T. It's important that there's a lot of pre-images for each target too. Okay, so I think now we're into the last. Well, I didn't define a lattice, but it's this SIS problem is a lattice problem. But now we're going to define a gadget. So this idea goes back to maybe like ITI in 1999 when he was optimizing these. But we're going to jump off at the construction from MP12. This is by Machancho and Pikert in a paper of theirs in 2012. It does many things, and one of these is optimization for these lattice trapdoors. Here, we're gonna generate this matrix A together with a trapdoor matrix R. It's this matrix with small random polynomials. We're going to construct it such that when we do vector matrix multiplication, we're going to get some row vector G here. That's it can really be anything such that SIS is easy to solve on this, and it's a little non-trivial. You can't just throw the identity matrix in here, because then say something with large coefficients won't have a small preimage, but usually this is going to be like a power of 2 vector, and we call this this matrix R here a G-trapdoor for A? Okay, so what does this actually look like? When you construct it, it's going to be this truly random A prime, and you're going to hide it in with this A prime times R. There's two ways to make this random or pseudo-random. The more efficient way is to do it with have this A prime times R be R LWE samples together with the first part of the matrix. Okay, so with this construction, it's fairly easy to map a pre-image for G to a pre-image of A. So let's see, got something in the chat. I should try to wrap up soon. Okay, I'm going too slow. Okay, so anyway, you use this as a linear map, and when you do this, it adds some skewing to the covariance, so it leaks information about the trapdoor. So you have to statistically hide it with a perturbation. I'm going much slower than when I practiced. So our main contribution is just mapping this to a family of entry lattices. So really quickly, the entry assumption is that if you take some two random polynomials with small coefficients in the ring and take one as the inverse multiplied by the other, this is pseudo-random. And we introduced together with a few co-authors, we introduced an inhomogeneous version of this where you shift by the gadget. So here R is again the small polynomial, E is a vector of small polynomials over the ring, and now G is just shifted by the gadget. And you'll notice that here the small polynomial R is almost a G trapdoor in this case. So really much of the work is applying the discrete Gaussian sampling framework to this offset case. So we have two trapdoors. One is approximate, one is exact. And in the approximate case, the analysis gets kind of tricky because the range of the SIS function, when you just plug things into the MP12 framework, you're going to have this inner product E with the pre-image X here, and this will leak information about E. So one of the contributions we have is a novel analysis that gives a way to do a perturbation in the domain and the range of the SIS function. And then memory-wise, this is roughly like half the size of the MP12 parameters for a fixed ring and modules. And also, this comes to complete parallelism down to the ring level. I say with pre-processing here, but it's also in the pre-processing because when you skew the sample, you're just doing it by a diagonal covariance. So that means when you perturb, you also have to perturb it out in a way and another diagonal covariance. Okay, and we also give an efficient implementation over in PALISADE. And we have the same thing, just with a little bit less parallelism. So this is an exact trapdoor. Exact trapdoor just means we correct the error, which means you can have a little bit smaller of a modulus. And yeah, the PALISADE implementation was, as you would expect, very efficient. So this leftmost is just a toy implementation, but everything else is, yeah, just, I think at least 100 bits of security from our estimate. And there's online and offline sampling. Offline is the perturbation sampling. These perturbations are independent of the pre-image, and they only depend on the trapdoor. So you can break it in two. And we also just compare with my paper with Ile and Pratier, where we, yeah, do have an implementation of MP12 in that paper. All right, thank you.
Okay, I guess we're running out of time, so maybe just push the question later or uh, just right on time. Yeah, so let's see if there is a question. Shashank, is there any question, or we can take them later if there is any.
I don't see any questions on Zeolab, and I don't see
Okay.
anything on Zoom either.
Okay, so let's maybe like start the next talk. Maybe it's a lattice-based IBE with equality test supporting flexible authorization in the standard model. So joint work by Jiangling Nguyen, Willy Susilo, Duang Huang Duang, Hui Guo and Hushun Guo. So the talk will be given by Jiang.
Yeah.
Can you please share your
Thank you
slide?
for your introduction. Can you see my screen?
No, not yet.
Is it now? Can you see?
Yeah, it started. Yeah,
okay.
Now it looks good. Okay.
So let's get started. So welcome to my section. So I will go first for the content. First, I will introduce our work, and then I will talk about the background and some building blocks. And then I will give the detailed construction, and then we will wrap up with the conclusion and future work. And as you can see from the name of our paper is a combination of identity-based encryption, the equality test, and the flexible authorization. So let's recall about the IBE encryption. The IBE encryption is the motivation of IBE encryption is to have the deployment of a public key infrastructure. So that's more generally in IBE can simplify the system that manages a large number of public keys rather than storing a big database of public keys. The system can either write the public key from the username or the email or the public key integer on anything. And then we will move on the equality test. The equality test comes from the demand that we should be able to compare two ciphertext without decrypt it. So this will help us to research the privacy and have the computation on the cloud database without review or have the risk of knowing some underlying message that the customer they don't want to share. And then after the equality test notion, we have the flexible operation that will enhance the equality test further by allow the owner of the ciphertext in controlling what messages they want to share. So you can see that we have three types of flexible operation. The type one is when the owner gives their authorization key, that means the trapdoor, to the receiver. They can perform the equality test between own ciphertext of their owner. On the type 2, they only be able to perform the equality test on specific ciphertext only. And on the type 3 is in the midst of type 1 and type 2. So that is the definition of IBE equality test and flexible authorization. Then let's talk about the application, the actual motivation of our paper. You can see that nowadays the IoT devices and also the sensor devices, we collect a lot of information about personal information, and then we upload it in the cloud. For example, here we have the health system, the smart health system. People in the community, they can wear some devices and tracking their information. And then usually it will be uploaded by a smartphone. And before the upload, we encrypted it and it will store in a database. Usually when if this database is managed by the government, then we will have a health officer to do some regular checks on all the people in the community. Then in that case, would they revealing actual information about sensitive information about community, he can use Taiwan to compare own information on the cyber test. For example, he can compute the statistic data in some the heartbeat or the temperature of the people in the community to check if there is something like a flu happen in the community or not. On another scenario, we can see that some medicine company, they want to advise new data, new medicine. Then they want to access to that cloud database too. And then if they have the trapdoor for only Taiwan, then he can compare, like get all the information from all the user. In that case, if we have the try 2 or try 3, then we will enhance the privacy protection further. And here we can talk about the security model. Here it's a typical security model for equality test. We have the one-way ID CPA. In this case, the adversary can have the trapdoor for target identity, and its goal is to review the plan test in the challenge cyber test. And in the indisputable ID CPA, the try-to adversary, he cannot have the trapdoor for the target identity. And its goal is distinguish which plan test is the challenge cyber test. So this is typical. And our contribution is we implement a concrete construction based on lattice. And our construction is executed in a standard model. You can see it here. We inherit now our work from multiple operations, and we introduce the first construction here, which is based on LWE problem. However, you can see that with the comparison here, we have the cyber test size increase and also the security increase. So our scheme may not really good yet, and it may be some not applicable in some scenario. Now let's talk about the building block. You can see here the lattice. Here, lattice is actually basically is a group of linearly independent vector, and these vector from basis for the lattice. And our work based on the LWE problem. The LWE problem is to distinguish is truly random or is it a form of this here a matrix with a static key and a noise A. And then we talk about the trapdoor. The trapdoor here we define it a trapdoor is a short matrix TA such that the trapdoor the matrix A multiplied with trapdoor A equals 0. And then we have some algorithm to generate the trapdoor along with the matrix and also with the symbol algorithm to extend that trapdoor. Now let's talk about detailed construction. Here we have the algorithm for our scheme, and it follow the full IBE scheme that introduced in IBE 10. And here we talk a little bit about the encryption that we introduce matrix R. The matrix R is served for two purposes. Is to combine the trapdoor for different type alpha flexible operation, and also it serves the purpose to in our reduction from LWE in our security analysis. So let's see about overview about cyber test structure. You can see it here. The R is a matrix stack support the flexible operation, and the C1 is in the cyber test of the M. The C3 is used to decrypt the C1. The C2 is the decryption of the collection resistant hash function here, and the C4 is used to decrypt C2. So C2 here actually is used for the equality test, and for the R combined with the C2 is to support the flexible operation. C9 is to ensure the integrity of the cyber test. In here, we will talk about our weaknesses. Here, in our security model, we do not consider the inconsistent packet attack. So after the half of our reviewer, we introduce a G5 to actually ensure the ciphertext integrity before execute the equality test.
Hello, Jiang, sorry to interrupt, but would you wrap up soon because
Yeah,
we're almost running out of time. Yeah,
it should be that.
thanks.
Yeah. And here we will talk about the matrix A in our reduction, but as you can see, my time is up, so you can go to our paper to see the full reduction. So for the future work, I think that if people interested, they can use another trapdoor to decrease the ciphertext size and also the frequency size, and also they can make a stronger security model. And thank you for your attention. I think that's all.
Yeah, I guess we do not really have much time for questions. So if there is any, we can discuss at the end. So I'd ask ask Jiang to, can you please stop sharing so that the next speaker is Orinjita, I guess. Orinjita, can you start sharing your screen? So the next talk is by Orinjita. It's a paper on efficient attribute-based proxy encryption with constant size ciphertext, joint work with S. Sharmila Deva Selvi and C. Panduragan. Orinjita, over to you.
Yeah, thanks, Pratyay. So today I'll be presenting our paper on efficient attribute-based PRE with constant size ciphertext. So what is proxy encryption? So it is a cryptographic primitive which enables a re-encryption of ciphertext under one public key towards another public key, such that with the help of a third-party proxy, such that the proxy should not learn any information about the underlying file. However, the traditional PRE only enables point-to-point communication. So there may be scenarios where it requires re-encryption functionality without the knowledge of the intended recipients. So to the rescue, Liang et al. Introduced the notion of attribute-based proxy re-encryption to enable fine-grained delegation of decryption rights, which enables many-to-many communication model. And such a primitive is very much applicable to data sharing in untrusted cloud storage applications. So here you can see an application of ABPRE. So in the context of attribute-based encryption, ABPRE is classified into the key policy ABPRE and the ciphertext policy ABPRE. We'll be only talking in the context of key policy, but the private keys and the re-encryption keys are captured by the access structure, and the ciphertext are labeled with attribute sets. So there are various properties of proxy encryption, that is PRE, and we'll be focusing only on two, which is the unidirectional, that is the re-encryption key enables transformation of ciphertext only from one access structure to the other, but not vice versa. And we'll be talking in the single hop setting where the ciphertext can be re-encrypted only once, and the re-encrypted ciphertext is called as the second level ciphertext. So here is the typical scenario of a first level encryption. This is an encryption, how the encryption syntax looks like in a public key setting. So you have the setup, key generation, encryption, and a decryption algorithm. So when you wish to do a re-encryption of the algorithm, of the ciphertext, you call the ciphertext as a second level ciphertext. So in order to do the re-encryption, you use a re-key generation algorithm to generate the re-encryption key, which will do the re-encryption from one access structure to the other, which will be fed to the proxy. Now the proxy will take as input this re-encryption key and the first level ciphertext to generate the second level ciphertext D. So the security game for an attribute-based proxy encryption scheme, which we show in our work, is in the form of a security game between the challenger and adversary. And we show in the selective security setting where the target access structure is specified beforehand by the adversary. And we have to show the security for both the levels, for first level and the second level ciphertext, where in the first level, you are going to encrypt a message chosen randomly by the challenger between M0 and M1 under attribute set W star, which models the target access structure. So this is for the first level, and for the second level, you have a second level encryption of the message. So the scheme is said to be in PRE CCA secure if the advantage of the adversary in guessing the message bit is negligible. So here is the security game. So we'll be talking in respect of a very important property of proxy encryption, which is collusion attack. So usually it is seen that the re-encryption key, which is generated, is a function of the secret key of the access structure of the delegator, the access structure of the delegator, and the delegatee. So it is a very natural question to ask if the secret key corresponding to the delegator can be somehow extracted from the re-encryption key. So it has been so seen that the proxy and the delegatee Bob, who has an attribute set W star satisfying m-row- of the delegatee, can collude to extract the secret keys of the delegator. So such a disclosure can cause complete compromise of privacy for the delegator, and collusion resistance is a very crucial property of KBAB-PRE. So we try to achieve KBPRE, collusion resistance in KBAB-PRE. So prior to our work, there were 2 attempts made by G et al. And Lee et al., who have achieved CCA, who claims to achieve CCA security and RCCA security respectively. We show that both the schemes are actually vulnerable to CCA attack and RCCA attack respectively. And we also proposed the first construction of a CCA secure KBAB-PRE scheme, however, in the selective model of security. And this is secure under the decisional bilinear Diffie-Hellman exponent assumption. And our scheme is based on the KBAB-PRE framework of Rao et al. And BLS short signatures. So I'll be just briefly going through how our scheme looks like. So here is a setup algorithm, which will choose the admissible bilinear pairing of groups G0 and G1 as the target source and target group of prime order P. And here you have 5 hash functions. So here you have the key generation algorithm. So we generate the private keys. An important feature of our scheme is that we achieve constant size ciphertext. So we achieve that by actually expanding the size of our private keys by a factor of the number of unique attributes associated with the access structure. So here is the key generation algorithm. So our encryption for the first level ciphertext is based on the hashed Elgamal encryption crypto system. So you compute the components C0, C1, C2, and C3, and you can see C4 basically as a BLS short signature on the previous components and the attribute set W. So this is my encryption. And for the decryption algorithm, we'll be using the same BLS signature to basically check the sanity of the ciphertext. And then here is the correctness given for the ciphertext. And we are going to recover the original message M. So here we have our re-key generation algorithm. So similarly, in order to achieve constant size ciphertext for second level ciphertext, we are going to increase the size of the encryption keys by a factor of the number of unique attributes associated with the delegator's access structure. So as you can see, the component RKI1I, here you have the keys associated of the delegator's access structure. So, and the value theta is actually chosen by the access structure of the delegator. So no one else will be able to actually acquire the value ki corresponding to the secret key of the delegator, because the value theta is chosen by the delegator himself. So this is the intuition as to why our scheme achieves collusion resistance. So here is how the re-key generation is done. And again, for the re-encryption, we'll have to first do a validity check for the re-encryption keys and this ciphertext and do the conversion as shown. And again, we'll do the re-decryption as shown over here with the given correctness. So our scheme actually achieves CCA security in the selective model, in the random oracle model, based on the n-decisional bilinear Diffie-Hellman exponent assumption. And also, if we can show that a scheme is unidirectional, if a scheme is CCA secure for first level ciphertext, it is collusion resistant as well. This is as per the theorem of Levert and Venoit. So you can see our for the full paper for further details of the proof. So just to conclude, I have shown that our scheme achieves CCA security, and we have also given 2 attacks on the previous 2 existing schemes in the literature on KPAB-PRE, and our scheme is selective CCA secure under the NDB-DHA assumption in the Arrow model. So that's all. Thank you.
Thank you. So do you have, I think we have time for one question. Do you have any, Shashank, in the chat?
Yeah, I don't see any questions in the chat, but I have one.
Sure.
Could we rekey from any policy to any other policy?
No, that has
Or
not.
Are there any constraints?
So there are no attempts made in that, but I guess that could be possible, given from an attribute set to an access structure. That could be that is a doable process, but it has not been attempted yet in the literature. But it is definitely achievable from one policy to the other. You mean to say a re-encryption key from one attribute to another access structure, something like that. So that should be doable.
So in the rekey procedure that you define, there are two policies taken as input, right? Can these two policies be arbitrary?
Yeah, it can be.
Okay, thank you.
Okay, thank you again. So I guess we'll move to the next talk. The next talk will be by Lindru Zhang. It's talk on adaptive, secure, identity-based inner product functional encryption and its leakage resilience. The joint work with Xianxian Wang, Yu Chen Chen, and Xu Ming Yu. So Lindru, please share your slide.
Okay.
Yeah, I need to maximize it, please.
Okay, so can you hear me?
Yeah, you're audible, but I think you need to maximize the slide. Yeah.
Oh, okay.
Yeah, now perfect. Please go ahead.
Okay, so thanks for the introduction. And I am Lin Ru, and I'm from the University of Hong Kong. So today I will talk about adaptive secure identity-based inner product functional encryption and its leakage resilience. Okay, so in this talk, I will first show some background about functional encryption and leakage resilient crypto. And then I will show our result and give some technical overview. So functional encryption was proposed to address the all or nothing problem of traditional public key encryption. And before the definition of FE appears, there were many works to overcome this problem. These works, including IBE, ABE, and PE, are considered as special cases of FE. So in an FE scheme, the key generator will generate a public key and a master secret key. And we can use the public key to do the encryption to get the ciphertext. And when we want to do the decryption, firstly, we should choose a function f. And then we call the key generation algorithm to generate a secret key for the function f. And finally, we can use the secret key to do the decryption to get a function value of the message fm. So informally, the security of functional encryption requires that one can't know anything about the message m except the function value fm. So after proposing the definition of FE, researchers started to build FE schemes for general circuits and some very powerful functions. But these FE schemes either have bounded collusion or have to rely on very powerful but impractical and not well-studied assumptions. Attacks were identified for some constructions that are based on I/O and multilinear maps. So recently, many works try to build efficient schemes for specific functions from well-studied standard assumptions. And most of them studied their work from inner product, which is simple but very useful. IPFE has many applications, such as computing the weighted mean. So it is important to make it more powerful and more secure. So here we develop identity-based inner product functional encryption by adding access control to IPFE. And in an IPFE scheme, the encryption algorithm will output a ciphertext for a vector X and an identity ID. And the key generation algorithm will output a secret key for a vector Y and an identity ID prime. And finally, the decryption algorithm will output the inner product value of vector X and Y only if ID is equal to ID prime. Now let's move to leakage resilient crypto. In traditional model, security usually relies on complete privacy of the secret key values, such as secret keys and randomness. Actually, as the development of side channel attacks have found that the adversary it's possible to get some information of the secret key values by capturing the physical nature of cryptographic operations. So leakage resilient crypto was introduced to provide formal security guarantees, even the adversary can get some information of the secret values. And the first step of achieving leakage resilience is to decide an appropriate model of what information of secrets the adversary can learn. In this paper, we considered the bounded retrieval model. So in the BRM, the amount of information can be leaked is bounded by an external parameter, and this leakage bound can be very large. Further, it requires that the efficiency of other parts of the scheme, except the length of the secret key, should be independent from the leakage bound. And many works propose different schemes under this model, such as PKE and IBE schemes. So in this paper, we first focus on identity-based inner product functional encryption and propose an IBIPFE scheme from DBDH assumption. Then we consider the leakage resilience of IBIPFE and propose a leakage resilient IBIPFE scheme in the BRM. And our scheme and a security proof built on hash proof system. And in our leakage model, an adversary is allowed to learn at most L bit knowledge from each secret key. And the leakage bound L can be very large. So firstly, our IBIPFE scheme is proved adaptive secure under DBDH assumption. And actually, the scheme can be viewed as an FE scheme for the following function. So the IND security of the IBIPFE states that the adversary who can query the secret keys for a set of ID and a vector Y can't distinguish which of the changed messages was encrypted under the condition that for all pairs ID and vector Y have been queried, it must hold that F ID star X0 ID Y is equal to F ID star X1 and the ID Y. Okay, so due to the time limit, we will focus on the second part of our result now. Many papers showed how to use a hash-proof system to construct leakage-resilient PKE and IBE schemes. But however, such HPS can't be applied to our cases directly. The reason is that IBIPFE requires that the decryption result only reveals an inner product value of 2 vectors and nothing else. But the encapsulation algorithm of HPS will output the encapsulated key directly. So when using such HPS to build a FE scheme, the decryption of FE will reveal the message vector other than an inner product value only. So in order to guarantee the security of resulting IBIPFE scheme, some modifications are needed on the underlying HPS definition. So here we developed the notion that identity-based inner product hash-proof system. And in an IBIP-HPS scheme, the valid or invalid encapsulation algorithm will take an identity ID as input and will output the ciphertext and an encapsulated key. And the key generation algorithm will output a secret key for a vector Y and an identity ID prime. And also the decapsulation algorithm will output the inner product value vector K and the vector Y only if ID is equal to ID prime. And this modification ensures that we can get a secure IBIPFE scheme from such IBIP-HPS scheme very easily by using the encapsulated key as a one-time pipe to encrypt a message vector. And as a benefit of it, we can move our focus from leakage resilience property of the FE scheme to the leakage smoothness property of the IBIP-HPS scheme. And we prove the following theorem. The theorem shows that if we have a leakage smooth IBIP-HPS scheme, then we can get a leakage resilient IBIPFE scheme in the BRM. So now we need to design an L-prime liquid smooth IBIP HPS scheme which meets the efficiency requirement of the BRM. As the first step to do it, we would like to design an IBIP HPS scheme from simple assumptions without the requirement of the liquid smoothness and the efficiency. And then we prove the following theorem to show that we can get a liquid smooth IBIP HPS scheme. Okay, so here we sum up our results. We first give the definition and some properties, and we propose an IBIP HPS construction based on our IBIP FE scheme. And then we show how to build a L-prime liquid smoothness IBIP HPS scheme. And also this scheme meets the efficiency requirements of the BRM. And finally, we developed the security definition of liquid resilient IBIP FE scheme in the BRM. And then we show how to build such a scheme from our liquid smoothness IBIP HPS scheme. Okay, so that's all. Thank you.
I do not really have time for questions, so I guess we just move to next talk and wait for the end of the session. So the next talk will be given by Sayantan Mukherjee on CCA Secure AB using tag and pair encoding. It's joint work with Olivier Blazy. Sayantan, can you please share your slide? I cannot hear you. I think you need to unmute.
Yeah. Hello?
Yeah, now it's fine. Yeah, please go ahead.
Okay,
yeah.
Great. Hello, good morning. So my name is Sayantan Mukherjee, and I'm going to give a talk on CCA Secure AB using tag and pair encoding. And this is a joint work with Olivier. So this talk is because I have only 5 minutes. This talk will just give brief idea of what exactly we have done. For better details, please check the actual video, longer video that is recorded, and please take a look at our paper. But let's start. So usually CCA security models the real world better because in CCA security we allow the adversary to have access to decryption oracle, and that actually very closer to the what we find in the real world. Now usually if one wants to convert a CPA secure scheme to a CCA security to achieve CCA security, it is usually costly because there are some generic tools like NIZK or verifiability, but those are quite costly. And what about the restricted class? So in this work, we focus on attribute-based encryption that are based on pair encodings only. Now, so let's talk about our motivation. So let's start from let's talk about few papers that are available in the literature. So the CGW in 2015 gave the first CPA secure ABE from predicate encoding. In 2016, Atravadum gave CPA secure ABE from pair encoding. Here I should mention that predicate encoding is weaker than pair encoding. So to know more about this kind of encodings, please take a look at our longer pre-recorded talk. So and then Chen and Gong in 2017 gave one CPA secure tag based ABE from predicate encoding. Now Chen and Gong's paper was their construction was extremely efficient because their construction was tag based construction. However, their construction could achieve only predicate encoding. So a natural question comes: what about pair encoding? Can one create a CPA secure tag-based ABE from pair encoding? So we asked this question in our paper, and at the same time, there was another paper by Chatterjee, Mukherjee, and Pandit in 2017 who constructed CCA secure attribute-based encryption from Atravadum's paper. That means that paper gave CCA secure attribute-based encryption from pair encoding. So in this paper, we asked the question that we merged both of the questions, and we asked the question, what about CCA secure tag-based ABE from the pair encoding? Is it possible or not? So here in this paper, we answer it to be affirmative. So let's first talk about pair encoding. So pair encoding has 4 algorithms. One is param, 2 encoding functions, and 1 pair function. So basically, param gives you the number of common variables, and then encoding 2 encoding function, 1 encoding key and 1 encoding ciphertext, encoding k and encoding c. So encoding k gives you 1 polynomial that will be used to create the secret key. Encoding c will outputs a set of polynomials that will be used to create the ciphertext, and pair outputs 2 matrices which somehow will be used to get back some alpha into s. So yeah, alpha into s0. So from this pair encoding, so just you don't have to go into the details. So just remember that there are 4 algorithms which give you certain kind of representations, and using those representations, we will be creating our ciphertext and keys, and at the end we will be decrypting our ciphertext using the keys. So let's go to our construction very rapidly. So this is the setup. Just first, if you can follow my mouse, like just notice that at the start we are running the param which gives n, and based on the value n, we are choosing some w's like w1 to wn. Other than that, we also choose something called w0 and w1 v2, and we choose a collision resistant hash function, and we give some public parameters which are basically commitments of the wi and vi. So you don't have to go to the details, but yeah. So this is our keygen and encryption function. So in the keygen, at first, just notice that there is this encoding function which gives the set of polynomials, and we choose some random variables, and then use those random variables to create the instantiate the polynomial in the group. So this way we create few keys, like few components of the keys. Similarly, in encryption also, we first run the encoding function, create the polynomial, then instantiate the polynomial or evaluate the polynomial for different variables, and we use create the ciphertext. Now here there is the notice that the difference from earlier work is that earlier usually the encoding function was used to create only one component of the ciphertext. Here what we are doing, we are creating 2 different components of the ciphertext. Now see this C1, this actually I have mentioned it in the longer talk as a in more details what exactly it does. So we use this C1, and we somehow we define another or rather we give out this C1, and somehow we want to cancel this C1, and for that we give something called W0 transpose into C1, so something like that. So it's so if you just go through the paper, it will be quite evident that why exactly we have done and how exactly we have done. And then we compute a commitment of all the available ciphertext components, and we create something called C0 dash, which is basically a commitment of all the ciphertext components. So anybody who changes the ciphertext will have a different C0 dash. So that's how we actually get the CCA security. And the decryption function, because we have added one extra component in the ciphertext, and yeah, so because we have added one extra component in the ciphertext, we had to modify the decryption function of available ABE based pair encodings, and this is our decryption function, and believe me, it works. And yeah, so let's conclude the talk. So we have constructed pair encoding based ABE with tags. Notice the point to notice here is that we could support multiple randomnesses in the secret key. We could support multiple randomnesses in the ciphertext, which was not possible if it was a predicate encoding. If predicate encoding was used to like in chain and gong paper, and we get CCA security paying very small price. But there is a catch in our construction, that our construction achieves security for pair encodings, which are a bit weaker secure pair encodings. And thank you. Thanks for your attention.
Okay, thank you, Shantan. So we have time for one question, I believe. Is there any? Shashank, did you see any? Or
No, I don't see any questions on Zeolab.
okay.
Does someone
Anyone
have
wants to ask a question? So
maybe
okay,
I
so
can
maybe
ask.
okay,
Okay,
sure,
yeah,
go ahead. Okay, I mean, my question is kind of very high level, conceptual level. So does tag serve any purpose in these AB constructions? Like it gives you some more simplification of something
Yes.
in general?
Yes,
Okay.
yes. So usually in case of tag-based construction, the constructions become quite efficient because the tags are, yeah. So and also the proof becomes quite simpler than the usual attributes paper. So yes.
And there is a generic technique to remove the tags, I believe.
This I cannot follow.
Okay, I see. I mean, like you need to go to like tag-based ABE to like full-fledged like standard ABE, right? Or is there?
No, not exactly. So tag-based ABE are
It's a different notion completely.
Yeah, it's a different notion completely. Yes,
okay,
yes.
Got it. Okay, sounds good. Okay, Shashank, maybe you can also ask the question.
Yeah, on the last slide, you mentioned that the notion of security you achieve is somewhat weaker for pair encodings. Weaker in what sense?
Weaker as in so it's like so in case of our pair encoding, so there are something called a lone variable and non-lone variable. In our case, we define, so usually pair encoding is a PMH security, right? So the master key hiding, perfect master key hiding security. So in our case, we had to define something called PMH star security, where we do not consider the non-lone variables. So we set the non-lone variables as 0, and we tell that okay, this still achieves some kind of PMH security, but because it is a little weaker than normal standard PMH security, we called it PMH star security, and that's why we say that the pair encoding is a bit weaker than the standard pair encoding.
Okay, yeah. Thank you.
So it will be a nice task to remove that restriction actually in the future.
Thank you.
Maybe you should stop sharing so that
the
next,
thank you. Thanks,
next speaker can start. Yeah. So the next talk will be by Alain Beshinley, and he'll give a talk about simpler construction of asymmetric primitives from obfuscation, a joint work with Hua Farshim and Georg Fuchsbauer. So Alain, please share your slide.
Yeah, I'm trying. I don't think it's working, is it?
It's not yet.
Oh, okay. Wait, I need to. What's going on? How do I get my browser to accept it? Okay, sorry. I need to change my system preference. No, come on. Okay, good. I think so. No?
Not seeing anything yet.
What's going on? I cannot add my. Okay, let me. My browser doesn't want to get to my screen.
Sometimes there are too many things open. You want to leave and rejoin, or?
No, I'll switch computer. Sorry about that. That's not. Okay, I'll be back in.
Sure. Yeah. Yeah. Maybe in the meantime, I can ask a question to a previous talk. Actually, it's a question on like lattice-based IB with equality test supporting flexible by Jiang. So you said like you're, so are you there, Jiang?
Yeah.
Yeah, so you said that you're constructing a standard model. So I wonder if you use random oracle instead, because if I recall in your table, there was no random oracle based lattice-based construction, right? So
Yeah.
so is there a construction that you can think about in random oracle model that's like more efficient or something?
I think that let me share my screen here. You're talking about this slide, right?
Right.
Yeah. And it's actually we follow the reduction and security rule from the IBEB10. So it's driven in the standard model, and also it's not trivial to convert to apply the technique from the IBB10 and others. So I need to introduce the magic R, and also it's a called the magic R. So that's the reason, because that's why our server test increase and the security increase.
I see.
So,
okay, thank you. Maybe you should, maybe you should stop sharing an LM.
Okay.
I'll be back with my other laptops. Can you just grant me the access when I'm ready?
Yeah. Can you try, please? Don't see anything yet. Elena, you're also mute, so cannot hear you as well.
Can you hear me? Yeah.
Oh, yeah. Oh, so there's 2 instances, I see. Okay, finally, it's coming. Awesome. Okay, please go ahead.
Okay, sorry about it. Okay,
yeah.
So I'm going to talk about this paper about alternative construction of asymmetric primitive from obfuscation. This is a work with Pouya, Farshim, and Georg Fußbauer. And so basically about the long title. So the thing is that actually I could put my screen, my camera as well. And so basically about the long title, so we build alternative construction in the sense that we obtain results that are already known from the similar assumption. We just propose new ways of getting them, and we focus on asymmetric primitives. So we build PKE, HIBE, and predicate encryption, and this is based on obfuscation. So the starting point of our work is the following simple PKE construction that is inspired by the witness encryption-based construction, and that we used also in an obfuscation paper in 2016. And so this PKE construction uses 2 ingredients. So the first one is a length doubling PRG, and the second one is an obfuscator. And so the construction is the following. So the secret key is just a PRG seed. The public key is just a PRG evaluation. And then to obfuscate, to encrypt a message using the public key, what you do, you just obfuscate the circuit that check that you know a pre-image of the public key. So an S such as GOS equal PK. And in which case the circuit returns the message, otherwise doesn't return anything. So it's actually very easy to show that this is a secure PKE scheme. Basically, what happens is that you can switch using the PRG security the public key to a random string, which is not in the PRG range with a good probability, and then the circuit always return button. So using IO security, you can show that the circuit that contains the message is indistinguishable from a circuit that doesn't contain any information about the message, and that you get CPA security. So the starting point of our work is that actually, if you check a bit the details, you can see that this is simple enough to be instantiated based on DDH. So we provide a statistical obfuscator for such a circuit using the DDH-based PRG. And so the thing we try to do in the paper then is to generalize this idea. So if you look at the construction again, what happens is that the obfuscated circuit that corresponds to a ciphertext is simply a circuit that checks if you know a preimage for some hardwired value, so where the hardwired value is the PRG evaluation on some seed. And so the seed is the secret part. And so the question is what happens if you use a different form of seed, and in particular, what happens if you define multiple seeds, and the seeds, you just need them to be pseudo-random. So what you can do is just define the seeds as being PRF evaluation for some PRF. And so you get a lot of seeds doing so. And so now, knowing the preimage for decrypting, it's the same as being able to evaluate the PRF on some input X. So doing so, you can generalize the circuit, the construction, and so you get now a setup that defines the master secret key, which is the PRF key. You get a public key that allows you to get these public keys that corresponds to PRG evaluation of PRF evaluations. And so now to encrypt, you do the same as before. You just obfuscate a circuit that outputs the message if you know the preimage for the public key, where the public key is the PRG evaluation of the PRF evaluations. And so now what happens is that, for instance, if you define a key gen process that outputs a PRF evaluation on some inputs, this gives you IBE. Basically, each ID will have only a fixed preimage for the PRG, and if you use this PRG evaluation on using this preimage, then you encrypt to this target identity. And so more generally, you can extend this ID to generate a particular key that allows you to evaluate the PRF on some subset of the inputs, for instance, using a constraint PRF, and then you get predicate encryption. And so actually, what you can show fairly easily is that if you use, for instance, a prefix fixing PRF, like GGM, you get bounded hive. And if you use a more general CPRF, for instance, CPRF for all circuits, you get predicate encryption for circuits. I'm cheating slightly here, but this is basically what happens. So, okay, so the main technical result of the paper, which I won't have time to talk about it, obviously, is how to get unbounded hive. So with the previous construction using GGM, you get bounded hive. And so the difficulty with unbounded hive is that the depth or the length of the target identity, of the challenge identity, is not bounded before setup. And so there are many challenges to do that based on obfuscation of circuits. So the first one is that circuits do not take unbounded inputs. So in particular, you cannot have unbounded identities using circuits. So to solve this issue, we use hashing to fix the length of the target identity. But the thing is that when you do hashing, you completely destroy the natural hierarchy that exists when you use hive. Usually you use a tree-based hash hierarchy, and so this completely destroys the hierarchy because it completely changed the way the identities are defined. And so to circumvent this issue, we add some layer of non-interactive proofs in the construction. And the last issue that comes up is that if you have unbounded IDs, you also have unbounded quantity of hardwiring to do in the security proof. So this is a bit more technical, but so this can be solved using pebbling. And so that's it for the talk. Sorry for the issues at the beginning.
Okay, thank you, Ellen. So, I mean, I guess we are at the end of the session. Yes, you ran out of time. I don't know if there is a room for any question. Srinivas, or should we just conclude?
Thanks, Pratyay. So if there aren't any questions, I think then then we can conclude the session. So thanks, Pratyay, Shashank, Shweta for chairing the session. So we'll be back at 6:30 p.m. India time or 1 p.m. UTC for the live sessions. In the meanwhile, you can view the streaming of pre-recorded sessions that is premiering on YouTube. I think that's all for now.
So thanks, Srinivas, and thanks, Pratyay, Shashank, and Shweta, and all the speakers.
Thanks a lot.